Hello, good students, and feel welcome. Want to continue with the series of differential calculus. And today I want to provide a question that is going to an extent, carries four concepts at a go. That is the first one. We are going to look at the area of intercepts. That is the first one. Then it's also going to carry the issue of stationary points and the nature of those stationary points, and also the sketch of the curve. So this question, by the end of our discussion, the question will have covered four areas. That is the area of intercepts, the area of stationary points, the area of nature of those stationary points, and of course also the area of curve sketching. So the question goes that the equation of a curve y equals to 2x cubed plus 3x squared. The equation of a curve is y equals to 2x cubed plus 3x squared. So the question goes, A, Roman 1, find the x-intercepts of the curve. Roman 2, you find the y-intercept of the curve. B, find or determine the stationary points. Then C, determine whether those stationary points are maximum or minimum. That is, determine the nature of those stationary points. Then lastly, sketch the curve. Now let's proceed. Now to work under this, I'm going to provide with this solution. The first one, the first question is asking about the x-intercept, and remember this, at x-intercept y is 0. So it is actually that we are taking that particular equation and then you're equating it to 0. Once we've equated to 0, we can use the approach of factorization so that we can get the value of x. So the common term here is x squared. We factor it out. Then we are remaining into bracket 2x plus 3. So here it means that x squared equals to 0, and therefore we'll take the square root, meaning x equals to 0, or 2x plus 3 equals to 0, which means if 2x plus 3 equals to 0, then it means this 3 can come to the other side to be negative 3. Then you can divide both sides by 2, and you're going to get that the next x is negative 1.5. Now we can write this x-intercept as coordinate form, where the first one is x is 0 and also y is 0. The second coordinate is x is negative 1.5 and y is 0. So these are the two coordinates that we require. That is the x-intercept coordinates. Once we have done with that, then we move on to the y-intercept. And remember this, at y-intercept, x is 0. And if x is 0, then we go back to the equation. Where there's x, we put 0. So y is equals to 2 into 0 squared plus 3 into 0 squared equals to 0. Because anything raised to 0 multiplied by 0 is 0. And therefore y is 0. If we can write it as a coordinate, the first value was x is 0 and y is 0. So the y-intercept therefore becomes to 0, 0. The coordinate of the y-intercept is 0 as 0. Now, once we have these intercepts, we can move on to the second equation, which was asking about the stationary point. So the second question is asking about the stationary points, and we know this, that at stationary point, dy over dx equals to 0. In other words, the gradient function equals to 0. So the gradient equals to 0 at stationary point. So what that question requires us to do is to differentiate that particular function, y equals to 2x cubed plus 3x squared. So then dy dx is equals to, we'll take this 3 back to multiply with 2, which we get 6. Then we subtract 1 from the power, which goes to 2. Then plus, take this one back to multiply with 3, it's 6. Then subtract 1, we get x to 1. So dy dx now is equals to 2 6x squared plus 6x. But remember, at stationary point, dy dx equals to 0. So I'm equating it to 0. Now, to solve this equation, of course, we can decide to divide here by 6, and here also by 6, and also here by 6. So that particular equation now reduces to x squared plus x equals to 0. We can use factorization approach, where the common term here is x, and then into x plus 1. So from here, it means x equals to 0, or x plus 1 equals to 0. So the first value of x is 0, and the second value of x is negative 1. Once you have the values of x, then we can substitute these values of x back to this original equation to get the values of y. So when x is 0, for this particular one, then you realize that y is also 0. So the first stationary point, therefore, is 0, 0. Now, secondly, when x is negative 1, again, we can substitute back here, and you can see that if we substitute negative 1 here and here, we get that y is equals to 1. And therefore, when x is negative 1, y is 1. So the coordinates of the stationary points, therefore, are 0, 0, or negative 1, 1. Then number C of the question was asking about the nature of those stationary points. But I want you to note this point before we go to them, that if the second differential of that particular function at the stationary point is negative, then that is a maximum turning point. Similarly, if the second differential at the turning point or coordinate, then that equals to 0, then that point is actually the point of inflection. And lastly, if the second differential at the turning point is positive, then it tells you that that particular turning point is minimum. Or else you can use the approach for maximum. You check the gradient to the left of the stationary point and to the right of the stationary point. If you find the gradient to the left of the stationary point is positive, then goes to 0, then goes to negative, then that becomes a maximum turning point. But if you find it is positive, relaxes to 0, then positive, then that is a point of inflection. Or if you find it's negative, then 0, then negative, again, that is still the point of inflection. But if you realize it is negative to the left, positive 0 at the center, that is 0 at the turning point, and then positive on the right side, then that becomes negative or minimum turning point. So you can either use this construction to determine by looking at the behavior to the left and to the right of the turning point, or you can approach it by use of the second differential, this one. If the second differential is less than 0, that's negative, it's maximum. If the second differential at the turning point is 0, it's the point of inflection. If the second differential at the turning point is positive, then that is a minimum turning point. Now we can proceed on now with our turning points. So remember this. What we have is the first differential is 6x squared plus 6x. So I want us to differentiate this particular equation the second time. Let's differentiate this particular equation the second time. Therefore, if we differentiate this, 2 will go back to multiply with 6, and that will gives you 12. Then you subtract 1, it remains x. Now here is power 1, you can subtract 1. So this one goes to 0, and then any number raised to 0 is 1, so 6 times 1 is 6. So the second differential, therefore, is 12x plus 6. Once you have the second differential, we can actually now start with the first turning point, negative 1, 1, at the second differential. So we are substituting the values of x at this particular point, that is 12 into -1 plus 6, which will be -12 plus 6. And if you take -12 plus 6, that gives you -6. And -6 is less than 0. And therefore, this particular turning point is maximum turning point. Similarly, we can also look at the second one. The second differential at 0, 0. Remember the turning point, the second turning point was 0, 0. So x is 0 here. We can substitute 0 here. So 12 into 0 plus 6, that will be 0 plus 6, which reduces to 6. And 6 is positive. That means 6 is greater than 0. And because 6 is greater than 0, then that particular point is a minimum turning point. So at that particular point, we have classified those particular turning points, either maximum or minimum. If you are to draw this one, then you are to see something coming up like this, then dropping. And if you are to draw this one, you'll see something coming up this way and then rising. So here we'll have a negative, not a negative, rather than a positive gradient, then a 0 here, then a negative on the right. Similarly, here you'll have a negative on the left, then a 0 on the center, and then a positive on the right. So if it's moving from a negative to a 0 to a positive, that is a minimum turning point. But if you are moving from a positive to a 0, then to a negative, that one is a maximum turning point. Now, the last one, which was actually the requirement of number D of our equation, was actually to sketch the curve. Now, we can start with this. First of all, you have to draw that particular curve by coming up with the axis, not to the scale, because this one you're just sketching. And then you can first of all locate your x-intercept. The first x-intercept I'm locating is -1.50. The other one was 0, 0. And then the next one is the turning points. Look at the turning points. The first turning point was -1, 1, which was maximum this way. That is maximum. And the other turning point was 0, 0, which was minimum that way. So what you do now, you take your pen or pencil with a bare hand and a smooth line, pass it through the x-intercept, let it go through the turning point, come it back to the other turning point, and take it again up that way. So you see the curve that is coming out is a cubic curve, and indeed the question had a cubic curve, that is y equals to 2x cubed plus 3x squared. So by so doing, we have sketched it. Remember, 0, 0 is the turning point, and the minimum, that is turning point, and the other one is the maximum turning point, that is -1, 1, and -1.50 is the x-intercept, as you can actually see there. So this is now the sketch of that particular curve. Good student, remember to subscribe to my class so that you can be notified whenever a new lesson is uploaded. Thank you for your time, and enjoy the discussion and also the lesson of mathematics. I appreciate for your time. Be blessed.